Okay, so then we will move on to the next presentation. So it's a great pleasure for me to announce Martin Ziegler from the TU Ilmenau. He will talk about bio-inspired information pathways. So please, Martin, the stage is yours.
Yeah, thank you, Regina, and thank you all already for joining. So I was asked from Rainer Waser to explain it a little bit more on a higher level. That's why I choose this title, Bio-Inspired Information Pathways. By the way, I would like to explain you one way we are doing the job as a kind of an idea how, as an engineer, you can approach this complexity of biology. And I like to start my talk actually with a statement which goes ahead with the speaker before me. So when you see what AI can do today, it's very brilliant. And this is a very, very simple example, I would say, for an AI system. When you ask an AI system to do this pattern recognition here of the traffic light, to just see this is a stop sign. Yeah? However, you can really easily cheat the system if you just putting a few of stickers on top of the systems and then comes to a misinterpretation. Yeah? So it means then the same algorithm will understand this as speed limit 45 miles per hour. I think it's from this American paper. And of course, when I sit in a car, and this misinterpretation can bring you in some uncomfortable situation. So my point is the same here as the speaker before me. It does not understand actually what it learns. And though the approach, what I like to show is to look a little bit how the brain, how biology is doing the job. And this is actually where I jump more than 10 years into the topic by looking onto the hippocampus. The reason for that is, since the hippocampus is this part of the brain which always sometimes is called the gateway to memory. It allows us to recognize, describing things, relating feelings to memories, and so on. And this is why people working over years, over decades, to better understand what's going on there, and they coming up with circuit schemes, topologies, and so on, how this kind of network will look like and how this network will work. And on a very abstract level, you may describe the functionality by two cognitive functions. The first function is called pattern separation. So if you have a difference in the input you make at the output, the difference is large. And the other concept, or the other cognitive function, is called pattern completion. You make the opposite. If you have a difference in the input, you make the output closer together. And when you're just looking to these two functions and you're just thinking on how you can bring this on a neural network, perhaps strategy seems to be very easy. So actually what you need to do this is a nonlinear transformation, doing this pattern separation job, and another one which doing this association or combining of distinct information, this pattern completion. However, seems to be very easy, but is far away from easy. Since this points to one of the most fundamental questions, I would say, I think in neuroscience, so how features are combined into a single experience. So how it works to do perception, cognition, and all the things we want to do. And why it's so extremely complicated at that point, since it seems on an abstract level, first of all, not so complicated. And this is when you take a closer look, or you can see when you take a closer look to the neural networks or the underlying structure. So actually you have temporal things involved, like the dynamics or stimuli, so inputs to the network, and also spatial things like the topology of the networks, and the topology of the networks is even growing. It's just changing over time. And if you look to that, what we typically do in, when we build an artificial neural network, we change somehow the topology and give then information to the network. And there is a kind of interaction between this kind of four things, which makes the things so complicated, yeah, and this kind of interaction, which may sort as a local mechanism which deals with this, is called plasticity or neural plasticity. And now, in my opinion, the way how to enter the problem from the cellular level is to mimic that kind of a processes, how to mimic a spatio-temporal patterns or dynamics. And there is a simple learning scheme, very old one, going back to Donald Hebb, this Hebbian learning scheme, which just state when two neurons are simultaneously active in such kind of a network, then they change their wiring. Yeah, in the simplest way, you can treat this as neurons that fire together, wire together, and this actually is a very simple way to deal with a problem with temporal spatial relations. And now, how the idea is how to do this in hardware, and this is straightforward here with this memristive devices. So for those who doesn't know what is a memristive device, it's a very simple device. You have two metallic electrodes, and between these two electrodes, a memristive layer, and now you apply a voltage, you change in different fashion here the atomic structure inside, and with that you change also the resistance of these devices. And actually what you get is something very similar, to what is here written by this Hebb learning rule. So actually you change with the conductance state of this device the connections between these two electrodes. And this is the way, of course, this function f is to figure out which kind of plasticity mechanism and which way it might work. But the idea is that you control the conductance state of the devices to control actually or to mimic the processes which occurs between the synapses. So actually now how this device looks like, and if you like to really bring this into reality, there are different approaches. They have all their pros and cons, and I just show you here one way to do this. It's a good playground, I would say, and a lot of people in the world using this. It's a redox-based memristive devices where you have transition metal oxides, different layer where you stack them on each other. And in this case, you have an inactive oxide or an active oxide. And now you can have different scenarios depending on the material itself. You can have some filamentary structure where you have a conducting path here through the devices, or you change here the position of this oxygen vacancies and therefore the resistance state. And more or less, what is the mechanism then? You change interfacial potentials, mostly as a Schottky barrier, and with that you change the resistance or the conductance of the device. Yeah, in our case, we're using here hafnium oxide and titanium oxide for these two oxide layers. So now the most important part for us as material scientists is now to change the stoichiometry or to mimic now the different, or to get the different switching characteristics. What you have to change is the stoichiometry, the content between hafnium and oxide. So if you have substoichiometric oxides, you will end there. If you have stoichiometric oxide, you have more interface or more homogeneous process. And we do this by magneton sputtering. So we're developing here a sputtering technique where we can control the substoichiometry of these devices. And this leads to these are IV curves, to different switching mechanisms. In one, we need inertial electroforming before we can use its area dependent, has a low retention. For this more filamentary-like devices, we get a relatively good retention. It depends on the area and electroforming. So now the point what I like to make with this is if we play with the oxygen vacancies in the materials, we can actually doing like that. We can control very precisely the conductance state as is perhaps required from this learning rules which I show to you. And we can improve even the quality of of the performance. If we introduce a small aluminum oxide barrier inside, then we need no electroforming at all. We have an intrinsic current compliance, and we can increase the retention, and the idea is here to better control the generation of oxygen vacancies here in the active hafnium oxide layer. And this allows us also to do a system integration, just in short, so we can integrate this into crossbar structures. And here's one example for a crossbar structure where you see the different resistance states depending now, can switch here binary from one state to another one. Okay, this is for material science, and I would say it's possible today to developing such devices where you can be precisely adjust the resistance state to mimic neuroplasticity. However, the important function or the important question, more or less what I'm like, no, I cannot answer the questions, but I like to give an idea perhaps how we're working on this is how to achieve now this higher brain functionalities with that. No? And actually, for that, I like to make your attention or put your attention to something very important in the developing of our brain, and this is the interaction with the environment. Yeah? And this is actually snapshots from neuron density of a newborn baby. Yeah, it was the same in your brain, and then after 1 month, 2 months, 2 years, 4 years. So means what you see is with 2 years, there is the highest density of neurons in the brain after this 2 years. And when you look to the development process after the birth, then you see there are kind of windows for learning sensory task, then motor language task, and perhaps higher cognition, so up to going perhaps to university or doing research. So the important point which I like to make here on that slide is if we design any neuromorphic system, so any system, artificial, bio-inspired system, what we have to think about when this system should have any interaction or higher cognitive function, we have to think about how he makes the interaction with the outer world. This is very important, perhaps outcome from this point. And here I give you a very simple example how you now may train a system to learn self-organized complex structure. And this is a model which is from Dante Chialvo and Ter Bak. And the idea is very simple. You have here a very simple neural networks with 2 layers, or should not have this structure, but just you have a simple neural networks. And what you try to do with this network, you like to treat the networks by changing here the connections to a state where it has the highest complexity. Yeah, and here I would say this is important first in the development of a brain when you have here some ordered structure like a lattice, or here you have something completely unordered, and the point where you like to end up is at the point where you have perhaps the highest complexity. Then this is for us a very interesting point. I will come later on this. So now how this model works very easily. So what you actually are doing is you set randomly all the connections, and then you teach the system by mistakes. That's why I call learning by mistakes. You just show him you just look which of this neural path is firing much. Then you look at the output. Look if the output is a desired one. If not, you prune out, you kill the connections, right? So for example, here this connection has built up as a maximum. Then you look, should this neuron the one who should fire? No. If not, you're just taking out, or you take it out with a certain probability. Yeah, so it's a very easy learning rule, I would say, but it allows to introduce a self-organized complexity in such kind of a structure. And actually what we have, or what we like to end up a little bit when with two system parameters, we have some kind of a control, or what we need is some kind of a control parameter of the system and something of the order parameters. So we like to reach the point where we have segregation and integration, or we say we have a balance between this pattern separation and pattern completion. This is the idea here. So now, how we can bring such kind of thing in hardware with devices. For that, I like to go back on the device level on plasticity and introducing something what we called stochastic or stochastic memoristic plasticity. So the idea is following. When you look up in a textbook very easily, then you will see that what is a definition of synaptic plasticity is a pristine increase in the synaptic strength following high activity. So this synapses which shows a high activity, so I interpreted this, has a higher chance to be strange or weakened, so to be changed here in this case. So now if we translate this to memoristic devices, this actually we use the probability that a device changes resistance state. This is the idea. Yeah? For example, when you look here onto this graph, we're taking voltage pulses to our single cell, and let's say we fix the voltage pulse height by 1 volt. So if we're just using a voltage pulse train with 5 pulses, the probability is more or less 0 to switch. Yeah? If we're using, however, 50 pulses, we get the probability to 100% that the device is switching. And actually, this we use as a learning scheme here for change the connectivity between the neurons. And just to motivate a little bit as a toy example, as a toy learning task, we put this network to learn facial expressions, but in a very simple way. We just say, okay, we encoded information, the eyebrow and the mouth, for example, and give this to the network, so different eyebrows looks and mouth looks, the network should combine to have something like, okay, she's looking happy or she's looking sad, for example, that kind of feeling. As a toy experiment. So we gave this on an ANN board. This is here a simple board where we have, in collaboration with Christian Wenger's group from EHP Frankfurt-Oder, they're developing CMOS integrated CMOS devices, memory arrays. They have 4 kilobits, and this board addresses those devices. This is our synapse, which we treat now with this plasticity rule. We use this synaptic pruning, so we use the probability of the measure that the device will change his resistance states, and we're using very simple binary neurons, which we lateral couple here with the winner take it all. So we have a lateral inhibition between the neurons here in the layer. So, and when we give this to this learning scheme, what you actually can see here after learning, we see the right outcome. So this network is able to learn this different facial expression as a very toy experiment. So if you're interested into more details, Christina it's one of my postdocs. She's here, she did all the work, and she also posted. So if you like to have more details, please look on the poster. Okay, from that point, it's a very simple, perhaps it's a toy experiment, perhaps, and for those people which doing very applications, perhaps, yeah, it's very simple, but it's give us perhaps an idea which way we might work. However, important point what I like to make is when we talk about the interaction with the environment, then the neural network is, if you like, is one part. The other part is the sensor. So how we do the feature extraction, so how we can put the information into our system. Yeah? Since, of course, if you have a good feature extraction mechanism, the network here can be very easy. If you're not having good sensor data and you're not getting out the right features, it's getting hard, or much more efforts you have to put to the neural network to do something with the data. So the data is very important. So, and actually, this is a strong motivation for us to play with this with the sensor part. And here's one, kind of sense we are very interested in, and this is hearing. And since hearing takes place, or a lot of them takes already place here on our inner ear, where the mechanical waves are then translated into an electronic signal, and this is here on the cochlea. And on the cochlea you have small hair cells which do with their motions actually the process of information translation from this mechanical signal into an electrical one. And why we are so interested into that, since when you see what our hearing can, it's really fascinating. So we can hear over a large frequency range from 20 hertz to 20 kilohertz with a high frequency resolution of 0. Up to 0.1% by 300 of around 300 of this hear cells, and we have a very large dynamical range. So we can hear the whistle of leaves, which is in the decibel scale, so something around 20 dB, and what it calls the threshold of pain when a fireworks explodes. Yeah? And these are 12 orders of magnitude in difference between the scales. And now think on a microscope which can has a resolution of 12 orders of 12 orders, yeah, with this high resolution in frequency. And the last point, it's adaptive. So when you now listen to me, or you make a conversation in a room where there's no noise, even for people which have problems in hearing, some hearing impairments, it's no problem. But when you do this in the coffee break, some people are really out of this. So we can also adapt to different environments, to different acoustic scenes. And one critical part is point to this dynamics of these hair cells. Then actually, these hair cells can treat as critical oscillators. No? Means when we operate them at their critical point, I mean what they're doing at the phase transition here at an oscillator, or at the bifurcation point between it's not oscillating and it's oscillating, then we have a strong nonlinearity and we have the highest sensitivity at that point. This is actually the idea, and what we get when we simulate that as a Hopf oscillator or as a critical oscillator is we have this high sensitivity and we have this nonlinear compressive amplification. Means when we have a very small signal here, yeah, the output is larger as for very high signal. Yeah, this is actually what is requested for this high dynamical range here. Okay, now the idea was to put this into hardware. How are we doing this? We're using here a MEMS system, as a micro-electromechanical system. This is a transducer. It's a silicon beam with integrated piezoresistive deflection and thermomechanical actuation. And we use an electronic feedback. This is our neuromorphic circuit. If you like, we take the sensor signal, multiply with factor A, a feedback factor, and an offset, and give this back to the sensor, to the actuator, and with this we can create a Hopf oscillator. So, and now, depending on this signal A, this is what you see here, for different sound pressure levels, what we see here when we go here at this critical point, we see this nonlinear sending at the active mode, this what we wish. And however, when we using a smaller feedback signal, we can push him away from this transition point, and we get a linear response, active or passive. So, and then sounds perhaps interesting. And we discuss this with colleagues from Fraunhofer IDMT, and they say, yeah, okay, then let's compare your microphone, if you like, with the best we have in our lab. And this is what they told us, are these measurement microphones. These are very bulky. You see this here. This is at Fraunhofer Labs. Here, very tiny. This is our MEMS system, and this is the measurement microphone. And actually, what we measure are different sound pressure levels. And here you see the gain. And the first good result was here is this 20 dB, yeah, what we as a human can hear, and we really reach here close to this 20 dB, so it's very close to this high quality measurement microphone, and it's an order of magnitude better as standard MEMS microphone, which are really over a long time on the market, and we have a dynamic range, what a normal microphone don't have, since due to the feedback factor, we can change the non-linearity or the gaining of this microphone. Okay, so far I only talk of one of these sensor beams. Of course, if I have only one, I treat them to one frequency, and we have 3,000 of these hair cells in our brain, and the reason is, of course, that we like to get a bandwidth, so from this 20 kilohertz to 20 hertz, yeah, and this is called tonotopy. It's like a FFT, what the hair cells, if you like, doing in our ear. So, and now the first things we have to do, we have to adjust the frequency of this MEMS resonators. This we can do, or what means easily, but we can do by changing geometry of these devices. So this will help us to change the frequency. And here is now a measurement with 7 of these beams for different frequency, and what you see is what we cover is something from 10 to 10,000 hertz, from 1,000 to 10,000 kilohertz. And what you see is we see a very high amplitude, which is very nice. Here you see a normal microphone, and this is the noise level. So we are working really above the noise level. But when you look here onto this figure, you might see also a problem with this concept. Since we have a good quality factor, since we have a good sensor, means we are very narrow in frequencies. So in principle, when a frequency comes in that interval, it will not seen, since the high resolution is only here at this spots. So actually, the point is we need something which we call tunability. We have to change also the frequency to really cover the whole bandwidth onto that. And the idea here is to couple hair cells or artificial hair cells to have a coupling mechanism in between. And here is a theory paper. We found this was actually the point where we jump in, or I jump into the topic, is actually, it's a little bit hard to see, when you're doing at bifurcation, the job at the bifurcation point, you see here a stronger response as when you are outside the bifurcation point. This is just the concept of sensing. However, when you couple Hopf oscillators, this is just simulations for normal Hopf oscillators, then you just to see two interesting things. The first thing is you see a synchronization, and you see, very important, a tuning to the bifurcation point. You have not to set really precisely the parameter A, the feedback parameter. It just self-organizing, go to the bifurcation point, synchronizing there, and have this high frequency component. So this leads us, or motivated us to see, okay, we have to look into the coupling mechanism between our sensors to increase the bandwidth and the frequency tuning at the same time. Here's how we're doing that, and here's just an example that it works with two of them. So actually in black, you see the uncoupled case, and if we increasing now the coupling tangent, you see you really get a stronger signal. We push it onto the signal, and also we see an increase also of the signal between these two resonance frequencies. So means the tune coupled oscillator to the bifurcation point with increased bandwidth. This is coming out here. Good. More or less last point for my talk. So far we're talking about the tensor. In the beginning I show you one example of a neural network, and we merge both. And if we like to merge both, yeah, actually this is what I explained to you. This is more or less what our sensor is doing. We have the transduction, we have the frequency decomposition, the nonlinearity, and what has been done here is something encoding, for example, into spikes. And this is actually what we have to think how we can encode this. And actually, what we mimic is the auditory nerve or the auditory sensing, where you have a membrane potential or the change here, yeah, and the potential we have, we like to map into a neural spike pattern to then use it in spiking neural networks. And when you look to that, what you actually can see is you have different kind of neural spike encoding which exist. You have a rate coding with an offset. You have here a latency time that it starts spiked, and you have something it's called adaptation. So the signal, the frequency goes down over time. And just really in short, this we are doing also with the circuitry. We have an encoding, we have envelope, and we're using here an integrate and fire neuron, and we have an adaptation circuit which actually doing this point. And this is actually the outcome. So if we have now a constant input, a constant membrane potential, which comes out from our sender, then we trigger here this spike events, and you see the adaptation, and it works with the input voltage. As stronger here the amplitude is, as stronger our signal is, as stronger is also our spike rate, what we find out. Well, this is, I think, standard here at the point. And the last point is this dynamic adaptation. So actually this is what you see here. We also can mimic this adaptation signal. That's in short. Okay, to have still a little bit time for the conclusion, as a take-home message. Bio-inspired IT, this is one of my important points perhaps, is we need external stimuli play a very essential role for learning. So we have to think about how the system interact with the environment to actually design a system perhaps which looks like this. You have the sensor with feature extraction and the neural network. I show you two cognitive functions or paradigms for self-organized complexity, pattern separation and pattern completion. Perhaps I'm convinced you that memoristic devices are good to emulate neuroplasticity in hardware to have spatiotemporal correlations. And yeah, the last about the MEMS cochlear. We call this MEMS cochlear as an adaptive acoustic neuromorphic auditory sensor. Not system is perhaps a little bit too much said here on this slide. Thanks to a lot of people, to a lot of founding sources we have for this project. Thank you for your attention. And if you're interested in learn more about bio-inspired pathway, we have here this book. It's for free. You can download this. All the chapters are on the internet. If you're just using here the link, you can have it and you can learn a little bit more about this. Thank you for your attention.
Yeah, thanks a lot, Martin. So the talk is now open for questions. Okay, so while we are waiting for questions, I did not really understand what was the oscillator in this cochlea.
Now we have a MEMS system where we take the signal and put it back on an actuator.
Okay.
And with that, we drive the
really
signal.
A mechanical oscillator.
It's a fully mechanical oscillator with an electronic feedback loop. And this drives, and this is actually where we're playing. We go to the bifurcation point, to the point where the oscillation starts, actually where the high sensitivity, without noise. Yeah, then when now a sound signal is coming to this, then it treats this to this nonlinear branch, and then we have a relatively high sensitivity. This is the trick.
Okay. So is it a commercial one, or is it so?
No, this is a home build. What
Homemade.
you see is the technology which we have in our clean room. This is our work. This is our playground, if you like. We play with the forms, with the materials, with the sizes, and so on.
Okay, so are there questions in the meantime? So people are moving. Okay, so if this is not the case, I would like to thank Martin again, and then we have a little bit time to assemble the next presentation. Thanks a lot.
Yeah, thank you.